Picture a time before stars, before galaxies, before light itself. The universe was a vast, silent darkness, stretching endlessly in every direction. This was the cosmic Dark Ages, a period so mysterious that even our most powerful telescopes struggle to peel back its secrets. But then, something extraordinary happened. The first stars flickered to life, piercing the void with their brilliant glow, and the universe as we know it began to take shape. These ancient beacons, born from the raw ingredients of the cosmos, hold clues to the very origins of everything around us. Yet their story is filled with puzzles so profound, they challenge our understanding of physics, time, and existence itself. What were these first stars like? How did they form in the emptiness of space? And why do their remnants scattered across the cosmos like celestial fossils still elude our grasp today? The answers lie buried in the faint echoes of light that have traveled billions of years to reach us. These are not just distant objects, they are the architects of the universe, the ones that forged the heavy elements in their cores, seeding the cosmos with the building blocks of planets, life, and even us. But for every discovery we make, a dozen new mysteries emerge. Some of these enigmas defy explanation, while others hint at forces and phenomena we've yet to even imagine. That's where our journey begins. Over the course of this exploration, we'll uncover 30 of the most baffling, awe-inspiring mysteries surrounding the first stars and galaxies. From the bizarre ways they might have formed to the ghostly signals they've left behind, each revelation pulls us deeper into the cosmic unknown. We'll venture into the realm of supermassive black holes that shouldn't exist, galaxies that appear too soon, and dark matter's invisible hand shaping the earliest structures of the universe. This isn't just a story about the past, it's a key to understanding our place in the cosmos and the incredible forces that shaped it. So, let's step into the darkness together and uncover the secrets of the universe's first light. The very first stars in the universe were unlike anything we see today. Born from a soup of hydrogen and helium, these ancient giants known as population 3 stars had no heavy elements to rely on, no dust or complex molecules to help them collapse into being. So how did they ignite in that primordial darkness? The answer lies in the extreme conditions of the early cosmos. Back then, the universe was far denser and hotter, with vast clouds of gas slowly gathering under gravity's pull. Without the cooling effects of heavier elements, these clouds had to reach incredible masses before they could fragment and ignite. Scientists believe these first stars could have been hundreds of times larger than our Sun, burning fiercely and dying young in spectacular supernova. But here's the puzzle: if they were so massive and bright, why haven't we spotted one yet? The light from these stars has traveled for billions of years, stretched and diluted by the expansion of the universe. What little remains is buried in the faintest whispers of infrared radiation, hidden behind layers of cosmic dust and newer, brighter stars. Even our most advanced telescopes, like the James Webb Space Telescope, are straining to catch a glimpse. Some researchers think these stars might have formed in isolation, making them even harder to detect. Others speculate they left behind ultra-dense remnants, like black holes or strange, hyper-energetic bursts that we're only now starting to recognize. The true nature of population 3 stars isn't just an academic curiosity. It's a missing piece in the story of how the universe evolved. Their explosive deaths scattered the first heavy elements into space, seeding future generations of stars, planets, and even life. Without them, the cosmos as we know it wouldn't exist, yet every theory about their formation raises new questions. Did they really form alone or in clusters? Could some have survived longer than we think, lurking in the farthest reaches of space? And if we do finally detect one, what other secrets will it reveal about the dawn of time? The hunt for population 3 stars is one of astronomy's greatest detective stories. These celestial pioneers should be everywhere after all. They lit up the universe, yet they vanished without a trace. The paradox is that we know they must exist because their fingerprints are all over the cosmos. The heavy elements they created, carbon, oxygen, iron, are woven into everything from planets to people. But catching a direct glimpse of these ancient giants, that's like trying to spot a single candle flickering on the moon from Earth. Part of the problem is time. The light from population 3 stars has been stretched by the expanding universe into the infrared spectrum, far beyond what human eyes can see. Even our best telescopes struggle to pick up these faint, redshifted signals amid the cosmic noise. Then there's the issue of distance. These stars formed just a few 100 million years after the Big Bang, meaning their light has traveled over 13 billion years to reach us. Along the way, it's been absorbed, scattered, and drowned out by younger, brighter galaxies that formed later. It's like listening for a whisper in a hurricane. Scientists have tried 2 main approaches to solve this mystery. The first is scanning the deepest, darkest corners of space with infrared telescopes, hoping to catch a trace of these stars' ultraviolet glow light that's been stretched into invisibility over eons. The James Webb Space Telescope, with its unprecedented sensitivity, is our best shot, but even its data is messy. What looks like a population 3 star could just as easily be a distant galaxy or a glitch in the instruments. The second approach is indirect, searching for the chemical signatures these stars left behind. When they exploded as supernova, they littered space with distinct elemental patterns. Some astronomers pore over the composition of the universe's oldest surviving stars, hunting for traces of population 3 material in their atmospheres. It's cosmic archaeology, sifting through stellar ashes to reconstruct the fire, but the challenges don't end there. If population 3 stars were as massive as we think, they'd have lived fast and died young, collapsing into black holes within a few million years. That means the window to observe them was astronomically brief. Even if we do spot one, it might already be long gone, its light only now reaching us from the grave. And then there's the strangest possibility of all. What if these stars didn't behave like we expect? Some theories suggest they formed in dense clusters, their combined light too diffuse to detect. Others propose they were surrounded by thick cocoons of primordial gas, hiding them from view entirely. Every dead end in this search forces us to rethink what we know about the early universe. Maybe population 3 stars weren't all monstrously big. Maybe some were smaller and longer lived, still lurking undetected in the cosmic shadows. Or perhaps their light is right in front of us, disguised as something else entirely. Until we find definitive proof, these stars remain both a cornerstone of cosmic history and one of its most frustrating ghosts. The answer is out there, written in the oldest light of the universe, waiting for us to decipher it. Between the fiery birth of the universe and the first glimmer of stars, there lies a shadowy chapter astronomers call the Cosmic Dark Ages. For roughly 100 million years after the Big Bang, the cosmos was a featureless expanse. No stars, no galaxies, just an ocean of hydrogen gas cooling in the expanding darkness. Without light sources, this era is literally invisible to our telescopes, a blank page in the universe's history book. But this darkness wasn't empty. Hidden within it were the seeds of everything to come, as gravity quietly sculpted the first fragile structures from the primordial gas. The darkness ended in a dramatic cosmic dawn known as reionization. As the first stars and galaxies flickered to life, their intense ultraviolet radiation began ripping electrons from hydrogen atoms, flooding the universe with light once again. This process wasn't instant. It unfolded over hundreds of millions of years, like a slow sunrise across the cosmos. Yet how exactly it happened remains one of astronomy's biggest puzzles. Were massive stars the primary architects of reionization, or did early galaxies play a larger role? Some theories even suggest black holes or exotic particles contributed to this universal transformation. Adding to the mystery, the timeline doesn't quite add up. observations of the most distant quasars' bright beacons powered by supermassive black holes reveal patches of ionized hydrogen earlier than expected. This suggests pockets of the universe woke up sooner than models predict, as if some regions couldn't wait for the cosmic alarm clock. Even stranger, the process seems uneven, with some areas reionizing faster than others. Was it a chaotic stop-start affair, or are we missing a fundamental piece of the puzzle? The answers are written in the faint afterglow of the Big Bang itself. By studying subtle ripples in the cosmic microwave background, the universe's oldest light scientists can trace how and when hydrogen was torn apart. But each new discovery deepens the intrigue. For instance, recent data hints that early galaxies might have been leakier than we thought, spewing radiation far beyond their borders. Others propose that dark matter's gravitational tug could have accelerated the process, creating hotspots of reionization. What's certain is this: the end of the Dark Ages set the stage for everything that followed. Without reionization, light couldn't travel freely, and the universe would have remained an opaque fog. Yet the more we learn, the clearer it becomes that this transition was messier, more violent, and far more mysterious than we ever imagined. The cosmic Dark Ages weren't just a pause, they were a crucible, and the forces that shattered them shaped the universe we call home. The epoch of reionization was like rewiring the entire universe, atom by atom, photon by photon. Imagine a cosmic game of dominoes where the first stars and galaxies set off a chain reaction that transformed the cosmos from a dense, opaque fog into the transparent expanse we see today. This wasn't a gentle process. Ultraviolet radiation from those early celestial powerhouses ripped electrons away from hydrogen atoms, ionizing them and clearing the way for light to travel freely across space. But here's the twist: this grand-scale light show didn't happen uniformly. Some corners of the universe woke up early, blazing with ionized bubbles, while others lingered in darkness for millions of years longer. What caused this patchy, chaotic transition? The debate hinges on two prime suspects: quasars and early galaxies. Quasars, supermassive black holes devouring gas at the centers of galaxies, are cosmic blowtorches, capable of ionizing vast regions with their intense energy beams. Some argue they were the primary engines of reionization, their radiation punching through hydrogen like bullets through fog. Others point to the collective might of countless early galaxies, each leaking UV light like a sieve. These smaller, more numerous sources could have slowly but surely flooded the universe with ionizing photons, like rain eroding a mountain over time. But observations keep muddying the waters. Deep field surveys reveal galaxies too faint to explain the scale of reionization, while distant quasars seem too rare to shoulder the burden alone. Perhaps the truth lies in an unseen synergy. Maybe galaxies did the bulk of the work, with quasars acting as cosmic accelerants in key regions. There's even wilder speculation. Could exotic particles or decaying dark matter have contributed extra ionization? The unevenness of the process adds another wrinkle. Some areas reionized rapidly, as if hit by a sudden wave, while others resisted like stubborn stains. This might trace back to variations in the density of primordial gas, or perhaps the clustering of early stars in certain regions created hotspots of radiation. The smoking gun might lie in the faintest signals from this era. Hydrogen atoms absorbing specific wavelengths of light leave telltale fingerprints in the spectra of distant quasars, a cosmic barcode revealing where and when reionization occurred. New telescopes are tuning into these whispers, but the data so far paints a messy picture full of contradictions. It's like trying to reconstruct a symphony from a handful of scattered notes. Every clue we uncover forces us to rethink our models, pushing us closer to understanding how the universe flipped the switch from darkness to light. Until then, the epoch of reionization remains one of cosmology's most tantalizing puzzles, a revolution written in the very fabric of space itself. We know the first stars were born from clouds of pure hydrogen and helium, pristine gas untouched by heavier elements. These primordial reservoirs should still exist as cosmic relics, floating through space like untouched time capsules from the universe's infancy. Yet despite decades of searching, not a single uncontaminated cloud has been definitively found. It's as if the universe cleaned up all traces of its own birthplace, leaving astronomers with a glaring absence where evidence should be. The challenge begins with the so-called redshift desert, a gap in our observational capabilities spanning a critical period between 800 million and 1 billion years after the Big Bang. During this era, the light from these ancient gas clouds gets stretched into an awkward middle ground, too redshifted for optical telescopes to see clearly, but not far enough into the infrared for dedicated instruments to pick up easily. It's like trying to tune a radio to a station that's perpetually stuck between frequencies, drowned out by static. Even the James Webb Space Telescope, designed to peer deeper than any instrument before it, struggles to isolate these faint, elusive signals from the cosmic background noise. But technology isn't the only hurdle. Theoretically, these pristine clouds should be rare. The first stars didn't just form, they exploded, seeding their surroundings with heavy elements. Supernova and stellar winds would have polluted nearby gas almost immediately, leaving only the most isolated pockets untouched. Some simulations suggest these untouched clouds might lurk in the voids between galaxies, where gravity hasn't yet drawn material together to form new stars. Others propose they could be hiding in plain sight, their signatures masked by younger, brighter objects in the same line of sight. There's also the possibility we're looking for the wrong thing. Pristine gas doesn't emit light. It only absorbs specific wavelengths when backlit by a brighter source like a quasar. Finding it requires a perfect cosmic alignment, a distant quasar shining through one of these invisible clouds, imprinting its fingerprint on the light. Even then, contamination is a constant worry. A whiff of heavy elements from a passing star or galaxy could spoil the sample, leaving astronomers debating whether they've truly found a relic of the early universe or just a slightly cleaner than average gas cloud. The stakes couldn't be higher. A confirmed detection would give us an unaltered sample of the raw material that birthed the first stars, letting us test our theories about their formation with hard data. It might even reveal surprises like traces of exotic physics or unknown processes that shaped the early cosmos. Until then, the absence of these cosmic fossils remains a haunting reminder of how much we still don't understand about the universe's first chapters. The search continues not just for the clouds themselves, but for the deeper truths they might unveil about our origins. If the first stars were the sparks that lit up the cosmos, dark matter was the invisible hand that arranged the kindling. This mysterious substance, 5 times more abundant than ordinary matter, doesn't emit, absorb, or reflect light, yet its gravitational grip is the unseen scaffold upon which galaxies are built. In the early universe, dark matter's role was especially dramatic. As tiny fluctuations in the primordial soup grew under gravity's pull, dark matter formed vast, tangled webs, with dense knots called halos serving as gravitational wells. Ordinary gas pooled in these halos, cooling and condensing until it ignited into the first stars and galaxies. Without dark matter's invisible architecture, the universe might have remained a formless void. But here's where the mystery deepens. Supercomputer simulations, like the famous Illustris and Eagle projects, show dark matter halos as cosmic nurseries, regions where galaxies should have formed in overwhelming numbers. Yet when astronomers peer back in time, they find far fewer early galaxies than predicted. It's as if the universe skipped half its building blocks. Some halos appear to have remained barren, gathering gas but never lighting up with stars. Why? One possibility is that the intense radiation from the first stars sterilized neighboring halos, boiling away their gas before it could collapse. Another theory suggests dark matter itself might behave differently on small scales, with properties that suppress star formation in certain halos. A handful of daring researchers even propose that dark matter could interact with itself through unknown forces, creating feedback loops that stunted galaxy growth. The discrepancies don't end there. Observations of the earliest galaxies reveal they're brighter and more massive than simulations anticipate, as if they grew up too fast. This too big, too soon problem hints that dark matter's role might be more complex than we thought. Perhaps the halos were denser, or maybe ordinary matter found ways to clump more efficiently in the early universe. There's even a fringe idea that primordial black holes left over from the Big Bang could have masqueraded as dark matter, seeding galaxy formation in unexpected ways. What's at stake isn't just a tweak to our models. Dark matter's fingerprints are all over cosmic history, and if we've misread them, entire chapters of the universe's story might need rewriting. The next generation of telescopes aims to map the distribution of dark matter in the early universe with unprecedented precision, looking for clues in the faint distortions of ancient light. Every new observation tightens the noose around this enigma, inching us closer to understanding how the invisible shapes the visible, and why the cosmos played by rules we're still struggling to decode. When the James Webb Space Telescope turned its infrared gaze toward the distant universe, it shattered expectations. Instead of finding small, fragile galaxies as predicted by cosmological models, JWST spotted sprawling cosmic cities, fully formed giants shining just a few 100 million years after the Big Bang. These galaxies weren't just early, they were impossibly mature, packed with stars and heavy elements as if they'd aged billions of years in a cosmic blink. The discovery sent shockwaves through astronomy, forcing scientists to confront a dizzying question. How could galaxies grow so large so fast? The implications ripple far beyond mere surprise. According to standard cosmology, structure in the universe builds gradually. Tiny fluctuations in the primordial soup grow under gravity, slowly accumulating gas and dust to form stars, then galaxies. For massive galaxies to appear this early, either our timeline is wildly off or some unknown process turbocharged their growth. Some theorists suggest dark matter halos might have been denser than we thought, funneling gas into galaxies with frightening efficiency. Others propose exotic mechanisms like supercharged star formation rates or mergers happening at unprecedented scales. A handful of researchers even float radical ideas. Could primordial black holes have acted as seeds, accelerating galaxy formation? Or is there a flaw in how we measure cosmic distances, making these galaxies seem more massive than they truly are? But the most controversial possibility is that the Big Bang itself might need rethinking. While not yet mainstream, a few voices argue these galaxies challenge the very foundations of cosmology. If the universe had more time to evolve than the 13.8 billion years we've calculated, it could explain the unexpected maturity. Alternative theories like the tired light hypothesis or cyclical cosmologies get whispered in conference hallways, though most astronomers consider them long shots. The prevailing view is that unknown astrophysical processes, not a rewrite of the Big Bang, will eventually crack the puzzle. What makes JWST findings so compelling is their consistency. These massive early galaxies aren't flukes. They're appearing in multiple deep field surveys, defying predictions across different regions of space. Their starlight composition adds another twist. Many show surprising levels of heavy elements, suggesting rapid cycles of star birth and explosive death. It's as if the early universe had a secret recipe for fast-tracking galaxy growth, one we've yet to decode. The race is on to reconcile theory with observation. New simulations tweak variables like dark matter interactions and gas cooling rates, hunting for combinations that produce giant galaxies quickly. Meanwhile, JWST continues collecting data, its infrared eyes peeling back layers of cosmic history with each observation. Every new discovery tightens the constraints, boxing in possible explanations. Whether the answer lies in revised physics, overlooked processes, or something entirely unexpected, one thing is clear: the early universe was far more dynamic, more inventive, and more mysterious than we ever imagined. Those massive galaxies aren't just celestial oddities, they're cosmic breadcrumbs leading us toward a deeper understanding of how the universe builds its grandest structures. Some of the most baffling objects in the early universe weren't stars or galaxies, they were supermassive black holes, lurking in the cosmic dawn with masses billions of times greater than our Sun. Their existence defies logic. According to conventional physics, black holes grow by slowly swallowing gas and merging with one another over eons. Yet when astronomers look back 13 billion years, they find these monsters already fully formed, as if they cheated time itself. How could gravity's most extreme phenomena have grown so vast, so fast? One leading theory suggests a shortcut: direct collapse. Imagine a vast cloud of primordial gas, so massive and dense that it skips the star-making process entirely. Instead of fragmenting into stellar nurseries, the entire cloud collapses in on itself, a catastrophic event birthing a black hole thousands of times the Sun's mass in one explosive step. These seeds would have had a head start, feasting on surrounding gas to balloon into supermassive giants faster than traditional models allow. But the conditions for direct collapse are extraordinarily rare. The gas must remain pristine, free of heavy elements that could cool it and trigger star formation, and it needs the perfect balance of turbulence and stillness. Even then, the process would require incredible cosmic fine-tuning. The alternative is a slower but more familiar path: stellar remnants. The first generation of stars were behemoths, some hundreds of times more massive than our Sun. When these stars died in supernova, their cores could have collapsed into black holes tens or even hundreds of solar masses. Over time, through constant feeding and mergers, these black holes might have snowballed into supermassive proportions. But here's the catch: there's barely enough time in the early universe for this gradual growth. Even with insatiable appetites, stellar origin black holes would struggle to reach the sizes we observe without some unseen cosmic boost. The debate gets even murkier when considering how these black holes intertwined with the first galaxies. Observations show a curious correlation: the more massive the galaxy, the heftier its central black hole. This suggests a symbiotic relationship where black holes and galaxies grew in lockstep, each shaping the other's destiny. Radiation from an active black hole could have heated surrounding gas, stifling star formation and regulating galaxy growth. Conversely, mergers between young galaxies might have funneled fresh material into waiting black holes, supercharging their expansion. But which came first, the galaxy or the black hole? The answer could rewrite our understanding of structure formation in the universe. New data only deepens the enigma. The James Webb Space Telescope recently spotted quasars, bright disks of material swirling around supermassive black holes, shining less than 700 million years after the Big Bang. Their brilliance implies black holes already weighing over 1 billion solar masses, a scale that strains even the most generous theories. Some researchers speculate these objects might have feasted on ultra-dense, dark matter halos or tapped into unknown energy sources. Others wonder if multiple black holes merged in cosmic hubs, creating anomalies of mass where gravity's rules bent to their will. Every possible explanation comes with trade-offs. Direct collapse elegantly explains the early giants but relies on near-mythical conditions. Stellar remnants fit our understanding of star life cycles but struggle with the math of rapid growth. What's clear is this: supermassive black holes weren't just passive byproducts of the early universe, they were active architects, shaping galaxies and perhaps even seeding the conditions for life itself. Until we unravel their origins, we're missing a fundamental chapter in the story of how the cosmos grew up. Stars from different cosmic eras carry distinct chemical fingerprints, like time capsules recording the universe's evolving recipe. The first generation, population 3, were pure hydrogen and helium giants. Later stars, like our Sun, are metal-rich, forged from the ashes of their predecessors. But between these extremes, there's a glaring gap. No stars with intermediate metal content have ever been found. It's as if the universe skipped a step, jumping straight from pristine to polluted without leaving traces of the transition. This missing link hints at a cosmic upheaval so violent it might have erased an entire chapter of stellar history. The leading suspect, hyperviolent supernova from the first stars. Unlike modern supernova, which leave behind neutron stars or black holes, these early explosions may have been pair instability events, cataclysmic blasts so powerful they completely vaporized the star, leaving no remnant behind. In this scenario, the first stars didn't just die, they self-destructed with enough force to sterilize their surroundings, scattering heavy elements far and wide while preventing the formation of intermediate metal stars nearby. Imagine a wildfire so intense it burns the soil beneath it, leaving nothing to regrow. These supernovae could have been the cosmic equivalent, clearing the galactic slate in their aftermath. But the mystery deepens when we consider the exceptions. A handful of ultra-faint dwarf galaxies, like Segway 1 and 2, contain stars with metal levels slightly above population 3 but still far below modern averages. These could be the survivors of that transition period, clinging to existence in isolated pockets where the supernova shockwaves didn't reach. Their scarcity suggests the process was brutally efficient, like a cosmic filter that only allowed the most extreme outcomes to endure. Alternative theories propose that the first stars didn't die alone. If they formed in dense clusters, their combined supernova could have created overlapping bubbles of hot gas, preventing new stars from forming until the metals were thoroughly mixed, skipping the intermediate stage entirely. Others speculate that radiation from early black holes or quasars might have suppressed star formation in metal-poor regions, creating a bottleneck in stellar evolution. The implications stretch beyond astronomy. If intermediate stars were systematically erased, we're missing a critical calibration point for understanding how elements spread through the early cosmos. This gap distorts our timeline of galactic chemical enrichment, like a clock missing its minute hand. Upcoming telescopes like the Giant Magellan Telescope aim to scour the Milky Way's halo for surviving relics, hunting for even faint traces of this lost generation. Until then, the absence of these stars remains a silent testament to the universe's most explosive growing pains. A cosmic revolution where the only witnesses were the elements themselves. The first heavy elements in the universe weren't just scattered. They were blasted into existence with unimaginable force. When those initial population 3 stars reached the end of their short, fiery lives, they didn't fade quietly. Instead, they detonated in supernova so colossal they could outshine entire galaxies. These explosions were the universe's first forges, smelting hydrogen and helium into heavier atoms like carbon, oxygen, and iron. But here's what baffles scientists. Instead of spreading evenly through space, these elements clustered in strange, uneven patches, some regions richer in metals, others eerily empty. This cosmic unevenness shouldn't exist if the first stars were distributed uniformly, so what caused the imbalance? One clue lies in the way these supernovae exploded. Unlike modern stars, which often leave behind dense remnants, the first stars may have undergone pair instability supernova, a rare type of explosion where the entire star is obliterated, flinging its newly forged elements far and wide. But even then, the debris wouldn't have spread uniformly. The early universe was a turbulent place with shockwaves from multiple supernovae colliding, creating pockets of dense metal-rich gas alongside vast, empty voids. Imagine tossing handfuls of sand into a stormy ocean. Some grains clump together while others vanish into the depths. That's the chaotic legacy of the first heavy elements. The distribution gets even stranger when we compare theoretical models to actual observations. Ancient stars in the Milky Way's halo, some nearly as old as the universe itself, show wildly varying metal content. A few are almost pristine, with barely a trace of elements heavier than helium, while others are surprisingly enriched as if they formed near a supernova's epicenter. This patchiness suggests the first metals didn't mix smoothly. Instead, they swirled through space in tendrils and bubbles, creating a cosmic mosaic where star-forming regions were either blessed with abundant materials or starved of them entirely. What's even more puzzling is how quickly these metals were recycled. Within a few 100 million years, second-generation stars were already forming from the ashes of the first supernova, but they didn't form uniformly. In some areas, metals acted like cosmic glue, helping gas cool and collapse into new stars faster. Elsewhere, radiation from the first stars might have prevented cooling, leaving potential stellar nurseries barren. This feedback loop, where metals both aided and stifled star formation, could explain why the early universe's chemical landscape was so uneven. The mystery deepens when we look at dwarf galaxies like Segway 1, which contain stars with metal levels far lower than expected. These cosmic backwaters might hold the key to understanding the transition from a metal-free universe to one teeming with heavy elements. If metals had spread evenly, these galaxies should have been more polluted. Their purity suggests the first supernova's debris didn't reach everywhere, or that some regions were shielded, preserving pockets of primordial gas like cosmic time capsules. The ultimate irony, these unevenly scattered metals became the building blocks of everything that followed: planets, life, even us. Without those chaotic, patchy supernova, the universe might have remained a monotonous sea of hydrogen and helium. Yet the very randomness that gave rise to complexity is also what makes it so hard to decode. As telescopes like JWST peer deeper into the past, they're not just mapping the distribution of the first heavy elements, they're uncovering the fingerprints of a universe that preferred chaos over order, and in doing so made life possible. When the first stars flickered to life, did they emerge alone in the vast cosmic darkness, or were they born within the cradle of fledgling galaxies? This seemingly simple question has torn a rift through astrophysics, with simulations and observations telling starkly different stories. On one side, supercomputer models suggest early stars formed inside dense knots of dark matter, protogalaxies taking shape in the universe's first structures. Yet when astronomers analyze the light from distant quasars, filtered through ancient gas clouds, they find traces of stars that seem to have lived and died outside any galactic structure. The contradiction forces us to rethink one of cosmology's foundational assumptions, that stars and galaxies grew up together. The case for protogalaxies comes from our understanding of dark matter's role. In the early universe, slight density variations in dark matter created gravitational wells where ordinary gas pooled, eventually collapsing into stars. Simulations like the Renaissance project show these early halos naturally birthing star clusters, cosmic villages that would later merge into cities we call galaxies. If this is correct, isolated stars should be vanishingly rare, since dark matter's pull would have corralled most gas into these growing structures. The chemistry fits too. Heavy elements from the first supernova would have been trapped within their host halos, enriching subsequent generations of stars in a closed cycle. But the universe loves a good paradox: quasar absorption lines. The barcodes left when ancient gas clouds filtered distant light reveal pockets of metal-free hydrogen floating far from any known galaxy. These pristine clouds shouldn't exist if all early stars were bound to protogalaxies. Even stranger, some show telltale signs of past star formation, faint imprints of ultraviolet radiation that could only come from massive stars that once shone nearby. It's as if entire stellar generations lived and died in the cosmic wilderness, their heavy elements lost to the void rather than recycled into new stars. One explanation pits two cosmic forces against each other: gravity versus radiation. The first stars were so luminous, their ultraviolet light may have heated surrounding gas to thousands of degrees, pushing it beyond the reach of dark matter's pull. In this scenario, some stars could have formed in the brief window before their own radiation sterilized nearby space, doomed to wander the cosmos without galactic anchors. Others might have been flung free by the violent kicks of supernova, ejected from their birth halos like embers scattered from a fire. The implications ripple across astronomy. If stars did form in isolation, their supernova would have peppered the early universe with rogue heavy elements, creating a patchwork of enriched and pristine regions. This could explain why some ancient stars, like the famous He0 1075,240, have barely a trace of metals despite forming relatively late. Their birthplaces might have been far from the pollution of galactic hubs preserved in cosmic backwaters. Alternatively, the quasar data could hint at a forgotten population of ultra-faint protogalaxies, structures so small and dim, our telescopes mistake them for empty space. The James Webb Space Telescope is now hunting for these ghosts. By searching for the faint infrared glow of early star-forming regions, it might finally catch a proto-galaxy in the act of assembly, or confirm that some stars truly did blaze alone in the darkness. Until then, the overlap between stars and galaxies remains one of the most tantalizing unsolved puzzles of cosmic dawn. The answer won't just rewrite our textbooks, it will reveal whether the universe's first light was a coordinated symphony or a chorus of solitary voices. When astronomers point telescopes at distant quasars, they don't just see a brilliant point of light, they see something far stranger. The light from these cosmic beacons passes through countless hydrogen clouds on its journey across the universe, and each cloud leaves a unique fingerprint, a dark line in the quasar's spectrum where hydrogen atoms have absorbed specific wavelengths. Together, these lines form what's called the Lyman alpha forest, a dense thicket of absorption features that maps the distribution of hydrogen across cosmic time. But this forest holds a puzzle. The patterns we see don't match what simulations predict about how matter should have been arranged in the early universe. Instead of orderly structures, we find chaos clouds with wildly varying sizes, densities, and temperatures, defying every expectation about how the cosmos organized itself after the Big Bang. The mystery starts with the forest's sheer complexity. In an ideal universe, hydrogen would have clumped predictably around dark matter halos, forming neat filaments and voids as gravity pulled everything into place. But the Lyman alpha forest reveals something messier. Some clouds are so dense they block nearly all the light behind them, while others are wispy and diffuse. Some regions contain overlapping absorption lines, as if multiple clouds are stacked along the same line of sight, while other stretches of space appear almost empty. This isn't just random variation, it's a sign that something fundamental about the early universe's structure is missing from our models. One leading explanation involves the turbulent aftermath of reionization. When the first stars and galaxies flooded the cosmos with ultraviolet light, they didn't just ionize hydrogen, they heated it, creating shock waves that rippled through the intergalactic medium. These waves could have stirred the primordial gas into frothy, uneven layers like bubbles in a pot of boiling water. Some regions would have collapsed under gravity, forming dense knots, while others were stretched thin by the expanding radiation fronts. If true, the Lyman alpha forest isn't just a snapshot of hydrogen's distribution, it's a fossilized record of the violent transition from darkness to light. Yet even this dramatic reshuffling doesn't fully account for the forest's quirks. Some absorption lines suggest hydrogen clouds are far colder than they should be, as if some unknown cooling mechanism siphoned away their thermal energy. Others hint at mysterious large-scale structures, gigantic cosmic walls that shouldn't have had time to form so early. The most baffling cases involve clouds so massive and dense that they defy explanation, appearing like cosmic roadblocks in a universe that was supposedly still smoothing itself out. The key to unraveling this mystery might lie in the relationship between dark matter and hydrogen. If dark matter particles interact with each other or with ordinary matter in ways we haven't yet detected, they could have sculpted the gas into unexpected configurations. Alternatively, magnetic fields from the first galaxies might have twisted and compressed hydrogen in ways that left lasting imprints. There's even speculation that primordial black holes drifting through the early cosmos could have gouged holes in the hydrogen distribution, creating gaps in the forest where none should exist. Each new observation adds another layer of intrigue. Recent studies using the James Webb Space Telescope have spotted Lyman alpha lines where none were predicted, suggesting pockets of hydrogen that survived reionization against all odds. Other surveys reveal strange correlations between cloud properties and the positions of distant galaxies, as if unseen forces link them across billions of light years. The forest isn't just a puzzle, it's a cipher encoding secrets about the universe's most formative era. Decoding it won't just explain why hydrogen clumped the way it did, it might rewrite our understanding of how the cosmos built itself from the ground up. At first glance, the early universe seems like it should have been a cauldron of heat radiation from the Big Bang. The searing birth of the first stars and the violent explosions of supernova all point to a cosmos bathed in warmth. Yet when astronomers examine ancient gas clouds through the lenses of quasars, they uncover a paradox: pockets of hydrogen far colder than our models say they should be. These frigid regions, some just tens of degrees above absolute zero, defy expectations, as if the universe's thermostat malfunctioned during its most energetic era. The discrepancy isn't just a curiosity, it's a crack in our understanding of how matter behaved when the cosmos was young. One clue lies in the peculiar nature of these cold clouds. They're often found in the cosmic equivalent of shadowed valleys, regions shielded from the intense ultraviolet light of early stars and galaxies. Without that radiation to heat them, these pockets of gas could have cooled through simple expansion, like steam condensing into water droplets. But that alone doesn't explain the extremes we observe. Some clouds appear too cold, as if an unseen coolant siphoned away their thermal energy far faster than ordinary physics allows. That's where dark matter enters the scene. Though it doesn't interact with light, dark matter's gravitational pull could have subtly influenced these gas clouds, stirring them in ways that promoted cooling. Some theories suggest certain types of dark matter particles might even collide with hydrogen atoms directly, transferring energy away like invisible refrigerants. The plot thickens when we consider the role of molecular hydrogen, a fragile molecule that forms when two hydrogen atoms bond. In the modern universe, this process requires dust grains as a catalyst, but in the primordial cosmos, dust didn't exist yet. Surprisingly, simulations show trace amounts of molecular hydrogen could have formed anyway, acting as a natural coolant. When these molecules collide with hydrogen atoms, they emit infrared radiation, carrying heat away into space. Even a tiny concentration could have accelerated cooling dramatically, turning warm gas clouds into cosmic iceboxes. The problem: we've never detected these primordial molecules directly. Their existence is purely theoretical, a ghostly explanation for a phenomenon we can't yet prove. Alternative explanations border on the exotic. Could primordial magnetic fields, weak but pervasive, have channeled heat away from these clouds? Or might unknown particles from the Big Bang's aftermath, relics like actions or sterile neutrinos, have interacted with hydrogen in ways we haven't anticipated? The most radical proposals even suggest modifications to gravity itself, arguing that the laws we take for granted might have operated differently under the extreme conditions of the early universe. The stakes are higher than they seem. If early gas was colder than predicted, it would have clumped together more easily, accelerating the birth of stars and galaxies in ways our models don't account for. This could explain why JWST keeps finding massive galaxies where none should exist. They had a head start thanks to cosmic refrigeration. Untangling this mystery isn't just about fixing a glitch in our simulations. It's about rewriting the recipe for how structure emerged in the universe. Every cold cloud is a relic, a frozen whisper from a time when the cosmos was still figuring out its own rules. And until we decode their chill, we're missing a critical chapter in the story of how everything, including us, came to be. Most stars today have companions binary systems where two stars orbit each other in a cosmic dance. But were the first stars also paired up? Recent simulations suggest these ancient giants might not have been lonely behemoths, but instead formed in twos or even small groups, locked in tight gravitational embraces. If true, this would rewrite much of what we assume about their lives, deaths, and ultimate legacy in shaping the early universe. The implications are staggering. Binary stars burn differently, explode differently, and leave behind radically different remnants than solitary ones. Yet proving this happened over 13 billion years ago is like trying to reconstruct a firework display from the ashes it left behind. The case for binary first stars hinges on the way gas behaved in the early cosmos. Unlike today's star-forming clouds laced with heavy elements that help them fragment into multiple small stars, primordial gas was pristine, cooling sluggishly as it collapsed under gravity. Early simulations assumed this would lead to single, monstrous stars, but newer models reveal a twist. Turbulence in the collapsing gas could have created whirlpools and eddies, splitting the cloud into two or more dense cores before ignition. These twin stars would have been born close together, sometimes separated by less than the distance from the Sun to Pluto, their fates forever intertwined. But binaries don't just change the number of stars, they alter their entire life cycle. A paired population 3-star could siphon material from its companion, growing even more massive and unstable than its solitary counterparts. Alternatively, tidal forces between the two might strip away outer layers, exposing their cores prematurely and triggering bizarre, asymmetrical supernova. The explosions themselves would differ too. In tight binaries, one star's supernova might engulf its partner, smothering it in a radioactive shroud or even kicking it free into space as a hypervelocity rogue star. The chemical aftermath would be equally chaotic. Instead of evenly dispersing heavy elements, paired supernova might launch them in focused jets or strange, lopsided bubbles, creating uneven pockets of enrichment that could explain why some regions of the early universe seem inexplicably metal-rich while others remain barren. The most tantalizing possibility involves black holes. If both stars in a binary collapsed into black holes, their eventual merger would unleash gravitational waves, ripples in spacetime millions of years before such events were thought possible. These ancient collisions might even account for some of the unexplained signals picked up by observatories like LIGO. Alternatively, if one star became a black hole while its companion lived on, the duo could have formed the earliest X-ray binaries, with the black hole devouring gas from its neighbor and glowing fiercely in X-rays. These beacons would have been rare but potent sources of ionizing radiation, potentially accelerating reionization in their corner of the cosmos. Yet for all these tantalizing scenarios, direct evidence remains elusive. The James Webb Space Telescope might spot hints, perhaps an overabundance of paired supernova remnants in distant galaxies or odd chemical signatures in ancient stars that point to binary enrichment. Until then, the question lingers, did the universe's first light come from solitary titans, or were its earliest stars born in pairs, their twin fates shaping the cosmos in ways we're only beginning to imagine? If binaries were common, the story of cosmic dawn wasn't just brighter. It was twice as complex. Gamma-ray bursts, those blinding flashes of energy visible across the universe, are nature's most violent spectacles. In mere seconds, they unleash more power than the sun will emit in its entire lifetime. But what if some of these cosmic detonations were the final cries of the universe's very first stars? The idea isn't just poetic, it's a plausible missing link in our search for population 3. When massive stars collapse, they don't always fade quietly. If they rotate fast enough and their cores are dense enough, they can launch jets of plasma at near light speed, piercing through their outer layers and triggering gamma-ray bursts. For population 3 stars, which were likely spinning rapidly and lacked heavy elements to slow them down, this scenario might have been inevitable. Yet here's the puzzle: despite scouring the skies for decades, we've never detected a gamma-ray burst with the unmistakable signature of a first-generation star. Simulations suggest these bursts would be longer and dimmer than modern counterparts, their light stretched and diluted by cosmic expansion. But even accounting for that, their absence is glaring. One explanation is that the first stars didn't die the way we expect. Without heavy elements to carry away heat, their cores might have collapsed directly into black holes without the explosive fireworks needed to produce a GRB. Alternatively, their bursts could be hiding in plain sight, disguised by intervening dust or lost in the noise of more recent explosions. The hunt has led astronomers to comb through archival data, searching for unusual bursts that might fit the profile. One candidate, GRB 090423, lasted just a few seconds but showed a peculiar afterglow hinting at an explosion in an environment nearly devoid of metals. Others, like GRB 130606A, displayed chemical fingerprints suggesting they originated in a universe less than 1 billion years old. Still, none have been definitively tied to population 3. The challenge is akin to identifying a single voice in a crowded stadium. The signals are there, but isolating them requires unprecedented precision. New telescopes offer hope. Instruments like the Swift Observatory and the upcoming Einstein probe are fine-tuned to catch the faintest, most distant bursts. Meanwhile, gravitational wave detectors might provide a backdoor solution. If population 3 binaries merged, their collisions could produce both GRBs and ripples in spacetime, a dual signature that would be hard to miss. Until then, the silence speaks volumes. Either we're looking in the wrong way, or the first stars died in ways we've yet to imagine. The answer won't just solve a cosmic mystery, it'll reveal whether the universe's earliest giants went out with a bang or a whimper. The cosmic dawn, that pivotal moment when the first stars pierced the darkness, was supposed to be a straightforward chapter in the universe's story. Conventional wisdom placed it around 200 to 300 million years after the Big Bang, a timeline supported by decades of simulations and indirect observations. But the James Webb Space Telescope has thrown that consensus into chaos, uncovering galaxies so mature and massive that they seem to demand an earlier start. Some now argue the first stars could have ignited as early as 100 million years post-Big Bang, a staggering shift that would force us to rewrite everything we thought we knew about how structure formed in the infant cosmos. This isn't just a matter of tweaking a few numbers. If the cosmic dawn began earlier, it implies the universe assembled galaxies at breakneck speed, condensing gas into stars and black holes with terrifying efficiency. Traditional models rely on dark matter's gradual pull to gather ordinary matter into clumps dense enough to collapse, a process assumed to take hundreds of millions of years. But JWST discoveries suggest something else was at work, perhaps a hidden population of ultra-efficient star-forming regions or even exotic physics that turbocharged gravity in the early universe. The implications ripple outward. An earlier dawn would mean supermassive black holes had more time to grow, explaining how some reached billions of solar masses so quickly. It could also push reionization earlier, reshaping our understanding of when and how the universe became transparent. Yet not all evidence points in the same direction. Observations of the cosmic microwave background, the afterglow of the Big Bang, still support the later timeline, with its snapshot of the universe's condition at 380,000 years old showing no signs of precocious structure. Meanwhile, studies of ancient quasars reveal patches of ionized hydrogen that align with traditional models, leaving astronomers grappling with contradictory data. Is JWST seeing a rare subset of unusually early galaxies, or is our entire cosmic chronology off by 100 million years? One radical possibility is that both timelines are right, but for different parts of the universe. Just as Earth's day begins earlier in Tokyo than in London, the cosmic dawn might not have been a single global event. Density variations in the primordial soup could have created early adopter regions where stars formed ahead of schedule while other zones lagged behind. This would explain why some quasars show fully ionized surroundings at surprisingly early epochs while other areas seem to have stayed dark longer. It's a messy solution, but the early universe was anything but tidy. The stakes are astronomical. If the cosmic dawn's timeline shifts, so does our calculation of how dark matter behaves, how quickly black holes can grow, and even the nature of the first stars themselves. Resolving this conflict isn't just about fixing a glitch in the models. It's about understanding whether the universe played by different rules in its youth, or if we've been missing a fundamental piece of the puzzle all along. As JWST peers deeper into the past, every new observation tightens the constraints, inching us closer to an answer that could upend cosmology as we know it. Among the countless stars that lit up the early universe, there may have been something far stranger lurking in the darkness, objects so bizarre, they defy everything we know about how stars work. These hypothetical dark stars wouldn't have shone by nuclear fusion like the Sun or even the first population 3 stars. Instead, they could have been powered by something far more elusive, the annihilation of dark matter. Picture a star not with a fiery core of hydrogen and helium, but with a heart of colliding invisible particles releasing energy as they obliterate each other. The concept sounds like science fiction, but it's a serious theory that could explain some of the most puzzling observations from the James Webb Space Telescope. The idea hinges on dark matter's peculiar properties. In the dense early universe, dark matter would have clumped into halos alongside ordinary gas. If certain dark matter particles like WIMP, weakly interacting massive particles, can collide and annihilate, they'd produce heat and radiation. In a massive enough gas cloud, that energy could counteract gravitational collapse, preventing fusion from igniting. The result, a star that glows not from fusion, but from dark matter's slow burn. These dark stars would be monstrous, up to 10 million times more massive than the Sun and 1,000 times wider, yet surprisingly cool and diffuse, their light spread across vast, hazy surfaces. JWST might already have glimpsed them. Some of the telescope's most intriguing early targets were inexplicably bright, redshifted objects that look like galaxies but could instead be single, gargantuan dark stars. Their spectra show unusual signatures, too smooth for a cluster of young stars, too luminous for a lone supergiant. If confirmed, these could be the smoking guns of a cosmic era where dark matter didn't just sculpt the universe, it powered it. Yet the theory isn't without hurdles. Critics argue that dark stars require a specific, narrow set of conditions: dense dark matter halos, the right particle interaction rates, and gas clouds that avoid fragmenting into normal stars. Even if they did form, their lifespan would depend on a steady supply of dark matter fuel. Once their local reservoir was exhausted, they'd collapse, possibly triggering fusion and transitioning into more familiar supermassive stars. The transition itself would leave behind chemical fingerprints, perhaps explaining why some ancient stellar populations show unexpected abundances of heavy elements. The hunt now hinges on distinguishing dark stars from early galaxies. Both would appear as faint, redshifted blobs, but subtle differences in their light could betray their true nature. Dark stars should emit a distinct thermal spectrum, peaking in the infrared with none of the telltale emission lines of star-forming regions. Upcoming JWST deep field surveys could settle the debate by catching these anomalies in the act. If they exist, dark stars would rewrite cosmic history. They'd represent an entirely new class of celestial object, one where the invisible scaffolding of the universe became its engine. More tantalizingly, their remnants could have seeded the first supermassive black holes, creating a direct link between dark matter and the monsters that lurk in galactic centers today. Until we know for sure, these phantom giants remain one of cosmology's most electrifying maybes, a testament to how much we still don't understand about the universe's first light. The first galaxies were supposed to be cosmic train wrecks, clumsy, misshapen blobs of stars and gas, barely held together by gravity. After all, the early universe was a chaotic place with violent supernova, swirling dark matter, and turbulent streams of raw material. Yet when the James Webb Space Telescope peeled back the veil of time, it revealed something astonishing: delicate spiral arms, sleek disks, and well-defined structures in galaxies barely 500 million years old. These weren't the disordered scraps we expected. They were shockingly polished cosmic sculptures, as if some unseen hand had meticulously shaped them ahead of schedule. This contradiction starts with our assumptions about galaxy formation. In simulations, the earliest protogalaxies emerge as lumpy, asymmetrical clouds, their stars scattered like shrapnel from an explosion. Without the stabilizing influence of heavier elements, their gas should have struggled to settle into orderly rotations, but JWST infrared eyes tell a different story. One standout example, the galaxy JWST 13-0, spins with the grace of a modern spiral despite existing just 300 million years after the Big Bang. Another, Sears 93316, flaunts a crisp disk structure complete with concentrated starlight at its core. How did these chaotic nurseries of gas and dust transform into such refined shapes almost overnight? One clue might lie in dark matter's hidden choreography. While ordinary matter clashed and churned, dark matter halos could have provided invisible scaffolding, their gravitational pull sculpting gas into stable orbits sooner than anticipated. Simulations that account for ultra-dense dark matter cores show gas settling into disks surprisingly fast, as if cosmic turbulence hit an unseen brake. Another possibility involves magnetic fields, weak but pervasive threads woven through the early universe. These fields might have acted like puppet strings, guiding ionized gas into orderly flows and preventing the violent fragmentation seen in simulations. Then there's the wildcard, mergers. We often picture galaxy collisions as destructive, but in the early cosmos they might have had the opposite effect. A series of gentle, glancing collisions between protogalaxies could have funneled gas into coherent disks, like ripples smoothing a pond's surface. JWST has spotted candidate systems where multiple small galaxies appear caught in the act of merging, their interactions stretching material into graceful arcs rather than chaotic splatters. The implications rewrite more than just galactic aesthetics. Structured galaxies mean stable environments, places where stars could form steadily rather than in frantic bursts, where planetary systems might have had time to take shape even in the universe's infancy. If these elegant shapes were common, the early cosmos might have been far more hospitable to complexity than we ever dared imagine. Yet every answer opens new questions. Did these galaxies retain their poise, or was this an ephemeral cosmic phase? JWST next deep surveys might reveal whether order was the exception or the rule, and whether we've underestimated the universe's knack for beauty from the very beginning. The universe is a master of cosmic accounting. Every simulation, every equation, tells us there should be thousands of tiny galaxies orbiting the Milky Way like fireflies around a lantern. Yet when astronomers tally them up, the numbers don't match. Over 90% of these so-called dwarf galaxies are missing, leaving a glaring void between theory and observation. This isn't just a small discrepancy, it's one of astrophysics' most persistent puzzles, forcing us to question whether our models are wrong, our observations flawed, or if some unseen force scrubbed the early cosmos clean of these galactic building blocks. At the heart of the mystery lies dark matter. According to our best models, the early universe was filled with countless small halos of dark matter gravitational traps where gas could pool and ignite into stars, forming the first dwarf galaxies. Supercomputer simulations like Via Lactea and Elvis show these halos swarming around larger galaxies like bees around a hive, their numbers dwarfing the handful of small galaxies we actually see. If the simulations are accurate, there should be hundreds more dwarf galaxies glowing faintly in the Milky Way's backyard. Their absence suggests something interrupted the process, stifling galaxy formation before it could even begin. One leading explanation points to reionization's brutal aftermath. When the first stars flooded the universe with ultraviolet radiation, they didn't just ionize hydrogen, they heated it, boiling gas out of small dark matter halos before it could cool and collapse into stars. Without fuel, these proto-galaxies would have remained dark and ghostly, invisible to our telescopes. Think of it like trying to light a wet match without dry tinder. The flame never catches. This scenario would explain why we see so few dwarfs today, but it's not the whole story. Some dwarf galaxies did survive, like the Large and Small Magellanic Clouds, suggesting that reionization was patchy. Some regions were sterilized, while others slipped through the cracks. Then there's the possibility that the missing dwarfs are out there, but we're just not seeing them. Many of these galaxies would be incredibly dim, their stars spread thin across vast distances. Current surveys might be missing them entirely, like searching for fireflies with a spotlight. Projects like the Vera C. Rubin Observatory aim to change that, scanning the sky with unprecedented sensitivity for ultra-faint dwarfs. Already, discoveries like Segway 1 and 2 galaxies so diffuse they were mistaken for star clusters hint at a hidden population lurking just beyond our detection. But the most radical idea challenges dark matter itself. If dark matter particles are warmer, that is, faster moving, then we assume they wouldn't clump as easily into small halos. This warm dark matter scenario would naturally suppress the formation of dwarf galaxies, aligning better with observations. The catch: it also risks disrupting other well-tested predictions, like the large-scale structure of the cosmic web. Alternative theories propose that dark matter interacts with itself or ordinary matter in ways that stripped gas from small halos early on, leaving them barren. The missing dwarfs aren't just a counting error, they're a vital clue in understanding how galaxies form and evolve. If they never existed, our models of dark matter may need a fundamental rewrite. If they're hiding, their faint light could rewrite the history of our cosmic neighborhood. Until we solve this puzzle, we're left with an unsettling truth. Either the universe is far emptier than we thought, or our eyes just aren't open wide enough to see what's really out there. Magnetism is a force we take for granted. It powers our compasses, shapes our technology, and even guides migratory birds. But in the vast emptiness of the early universe, magnetic fields shouldn't have existed at all. The Big Bang's searing heat would have scrambled any primordial magnetism, leaving the cosmos a blank slate. Yet today, magnetic fields weave through galaxies, galaxy clusters, and even the voids between them. This raises a profound question. When and how did the universe's first magnetic fields emerge, and what role did they play in shaping the cosmic dawn? Theories split into two camps. One argues for exotic origins, fields born from the chaos of the universe's first moments. In this scenario, quantum fluctuations during inflation, the brief period of exponential expansion after the Big Bang, could have imprinted weak magnetic seeds across space. These fields, barely a trillionth the strength of a fridge magnet, might have grown as the universe expanded, amplified by the motion of ionized gas during structure formation. If true, magnetism was there from the start, quietly guiding the flow of matter into the first stars and galaxies like invisible rivers shaping a landscape. The other camp places the birth of magnetism later, in the violent aftermath of the first stars. When massive stars exploded as supernova, their shockwaves could have generated turbulent dynamos in the surrounding gas, sparking localized magnetic fields. Over time, these patches might have merged and strengthened, spreading through galactic winds or the cosmic web. This stellar origin story fits with observations of young galaxies, where magnetic fields often align with star-forming regions. But it struggles to explain why even the most remote void regions far from any star show traces of magnetism. Clues might lie in the universe's oldest light. The cosmic microwave background, a snapshot of the universe at 380,000 years old, holds subtle hints of primordial magnetism. Some studies claim to detect faint polarization patterns that could only come from early magnetic fields, though the signals are buried in noise. Other evidence comes from distant quasars whose light passes through ancient gas clouds. If those clouds were magnetized, they'd twist the quasar's light in a telltale way, an effect called Faraday rotation. A handful of observations suggest this twisting exists at redshifts as high as 7, implying magnetism was already widespread when the universe was less than 1 billion years old. Yet the strongest case for early magnetism comes from an unexpected place: the structure of galaxies themselves. Simulations show that without magnetic fields, gas collapsing into proto-galaxies would fragment chaotically, creating clumpy, irregular shapes. But when primordial fields are included, they act like cosmic scaffolding, channeling gas into smoother disks and filament structures eerily similar to the elegant spirals JWST has spotted in the early universe. This doesn't just solve a mystery, it suggests magnetism wasn't a passive player in cosmic evolution but an active architect, shaping the blueprints for everything that followed. The implications ripple far beyond astrophysics. If primordial fields exist, they could be relics of physics beyond the standard model, offering a window into phenomena like extra dimensions or grand unification. Alternatively, if magnetism arose later, it would mean the universe engineered its own invisible forces through sheer chaos, turning stellar explosions into cosmic looms weaving magnetic threads across the void. Either way, the answer holds the key to one of cosmology's quietest yet most pervasive puzzles: how an unmagnetized universe learned to wield this force, and why it's written into the fabric of everything we see. The universe's first stars didn't just vanish without a trace. Their collective glow still lingers, a faint whisper of light woven into the fabric of space itself. This stochastic background, the cumulative radiation from every early star that ever burned, should paint the cosmos with a subtle but detectable haze. Yet when astronomers measure it, the signal is mysteriously dim, as if something in the void is absorbing or scattering this primordial light. The discrepancy isn't just a technical hiccup. It hints at hidden processes in the early universe, processes that might rewrite our understanding of how light traveled through the infant cosmos. Picture this background glow as the universe's oldest photograph, a blurry snapshot of its first cities of light. Simulations predict that the combined ultraviolet emission from population, 3 stars and their descendants should create a distinct infrared signature, redshifted by cosmic expansion into wavelengths we can detect today. But observations from telescopes like Spitzer and Hubble fall short, missing up to half the expected signal. Where did all that light go? One possibility is that vast clouds of neutral hydrogen, left over from the cosmic dark ages, acted like a celestial fog, soaking up ultraviolet photons before they could contribute to the background. These primordial gas pockets, nearly invisible to our instruments, might have been far more abundant than we thought, creating a patchy filter that dimmed the early universe's glow unevenly. But gas alone might not explain the full deficit. Another tantalizing culprit lurks in the realm of exotic physics, decaying dark matter. If certain hypothetical particles like actions or sterile neutrinos were unstable, their breakdown could have produced just enough extra radiation to ionize hydrogen atoms, effectively recycling the missing starlight into forms we can't easily detect. It's a radical idea, but it would solve multiple puzzles at once, not just the faint background, but also anomalies in the cosmic microwave background and the unevenness of reionization. The irony is delicious. The very substance we call dark might have stolen the universe's first light. Then there's the wild card, dust. Conventional wisdom says dust didn't exist yet in the early universe. It requires heavy elements forged in stellar furnaces. But what if the first supernova produced tiny grains of carbon or silicon faster than we've assumed? Even trace amounts of dust could have a dramatic effect, scattering ultraviolet light like a cosmic haze, redirecting it into wavelengths that blend seamlessly with the infrared background. Recent JWST observations of surprisingly mature galaxies in the early universe lend credence to this idea. If dust appeared earlier than expected, it could be the ultimate cosmic prankster, hiding the stars' collective glow in plain sight. The hunt for answers is pushing telescopes to their limits. By cross-referencing data from gamma-ray bursts, quasar spectra, and deep field surveys, astronomers are piecing together a map of where the missing light might be hiding. Some propose it's tangled in the filaments of the cosmic web, its energy dissipated across vast intergalactic distances. Others suggest it was cannibalized by early black holes, their voracious appetites converting starlight into gravitational energy. The truth might be stranger still. Every flicker of this background light is a message from the universe's youth, and decoding it could reveal not just where the light went, but what the cosmos was really like when it first turned on the lights. The universe's recipe book has a glaring typo, one that threatens to rewrite our understanding of the Big Bang itself. According to every calculation, the first few minutes of cosmic existence should have cooked up precise amounts of hydrogen, helium, and lithium, with the lightest metal, lithium, appearing at a ratio of about 1 atom for every 10 billion hydrogen atoms. Yet when astronomers analyze the oldest stars in our galaxy relics, nearly as ancient as the cosmos, they find 3 to 5 times less lithium than expected. This discrepancy, known as the lithium problem, isn't just a minor accounting error. It's a cosmological crisis that forces us to question whether we've misunderstood stellar evolution, the earliest moments of creation, or both. One possible culprit lies in the hearts of the first stars. Population 3's behemoths burned at temperatures and pressures far beyond anything in the modern universe, creating environments where lithium could have been easily destroyed. In normal stars today, lithium survives in the cooler outer layers, but these primordial giants may have mixed their interiors so violently that lithium atoms were dragged into their cores and obliterated in nuclear reactions. When these stars eventually exploded, they would have scattered their lithium-depleted ashes across the cosmos, contaminating subsequent generations of stars with lower than expected amounts of the element. It's a compelling explanation, except for one hitch. Even the most metal-poor stars we've found, which formed from gas barely touched by population 3 supernova, still show the same lithium shortfall. If the first stars aren't to blame, where did the lithium go? That's where the plot thickens. Some theorists argue the problem isn't with stars at all, but with our models of the Big Bang. The calculations predicting lithium abundances rely on notoriously tricky nuclear reaction rates, especially the conversion of beryllium-7 into lithium-7 in the early universe's cooling plasma. Tiny errors in these rates could throw off the entire prediction. An even more radical idea suggests unknown particles from the dawn of time, like hypothetical dark photons or other relics, might have altered the nuclear balance, either by destroying lithium or preventing its formation in the first place. These proposals venture into uncharted physics where the rules of the standard model might not apply. Yet another camp suspects lithium isn't missing at all, it's just hiding. Inside ancient stars, convection currents could have dragged lithium deep below the surface where our telescopes can't detect it. A handful of stars, like the 11-billion-year-old Kappa Ceti, show lithium abundances that fluctuate over time, as if the element is periodically dredged up from hidden reservoirs. If this process is common, the lithium deficit might be an illusion, a trick of stellar chemistry rather than cosmology. The stakes couldn't be higher. Lithium is more than just the third element. It's a litmus test for the Big Bang itself. If standard nucleosynthesis calculations are wrong, it could mean our entire timeline of the universe's first minutes is flawed. Alternatively, if population 3 stars really did erase lithium, their fingerprints would offer a unique window into the behavior of these elusive giants. New telescopes, like the extremely large telescope nearing completion in Chile, aim to measure lithium in even older, fainter stars near the edge of the observable universe. Until then, the lithium problem remains a cosmic whodunit, one where the suspects range from stellar physics we don't fully understand to laws of nature we haven't yet discovered. Could planets form around stars that had no metals, no silicon, no iron, no carbon? The idea sounds impossible at first. After all, modern planets like Earth are built from the heavy elements forged in stellar furnaces. Yet the first stars were pure hydrogen and helium, leaving nothing solid to clump into worlds, or so we thought. Recent simulations reveal a startling possibility. The universe's first planets might not have been rock or iron, but something far stranger, worlds sculpted from carbon with diamond crusts and tar-filled atmospheres. Picture a star 100 times more massive than the Sun, blazing furiously for just a few million years before exploding. In its final moments, its core would fuse helium into carbon at a staggering rate, creating vast clouds of soot-like particles. If these carbon flecks clustered together under gravity, they could have coalesced into planets before the star's supernova scattered them across space. These carbon planets would be unlike anything in our solar system, surfaces of graphite or even diamond, oceans of liquid hydrocarbons, and atmospheres thick with methane and cyanide. Theoretical models suggest they could grow to several times Earth size, their interiors compressed into exotic crystalline forms by intense pressures. The real shocker, a few might still exist. While most first-generation planets would have been vaporized by their host stars' violent deaths, some could have been flung free into interstellar space as rogue worlds. Others might orbit the ancient white dwarfs or black holes that remained after population 3 stars died. The trick is finding them. Carbon planets would be nearly invisible in optical light, but their infrared signatures leaking heat from deep within their layered interiors could betray them. Projects like the James Webb Space Telescope are scanning metal-poor stars in our galactic halo for the faint wobbles of orbiting bodies, while others hunt for the reflective glint of diamond-rich surfaces in the glare of pulsars. But the wildest twist comes from closer to home. Some astronomers speculate that a handful of bizarre exoplanets already discovered, like 55 Cancri, a world once hypothesized to have a diamond core, might actually be survivors from this early era. Their extreme densities and carbon-rich spectrums don't match modern planetary formation models, but they'd fit perfectly with the ashes of the first stars. If true, these ancient worlds could be time capsules, preserving the chemistry of the universe's infancy in their crystalline hearts. The implications rewrite planetary science. If carbon worlds formed around metal-free stars, planets didn't have to wait for generations of supernova to provide ingredients. They were part of the cosmic story from the very beginning. That raises an even more profound question. If life requires carbon and carbon planets existed first, could the universe have gotten a head start on creating it? The answer, like these phantom worlds, remains hidden in the darkness, waiting to be uncovered. The reign of the universe's first stars couldn't last forever. Like a fire consuming its fuel, their era had to end, but how? Pinpointing the moment population 3 stars stopped forming is like trying to catch the last note of a song echoing across billions of years. Did they flicker out one by one as the cosmos evolved, or was their demise sudden, cut short by some cosmic upheaval? The answer isn't just about stellar obituaries, it's a clue to how the universe transitioned from simplicity to the chemical richness we see today. One school of thought suggests a slow, inevitable fade. As these massive stars died in supernova, they polluted their surroundings with heavy elements, altering the cosmic landscape forever. Gas clouds that once collapsed into pristine giants now had traces of metals carbon, oxygen, silicon that allowed them to cool and fragment more efficiently. This shift birthed smaller, longer-lived stars, crowding out the conditions needed for new population 3 stars to form. Imagine a forest where towering redwoods once dominated until their fallen leaves enriched the soil so much that only smaller, faster-growing trees could thrive. The universe might have followed a similar path, its chemistry evolving until the age of giants was simply no longer possible. But there's a competing, more dramatic possibility, a sudden cutoff. Reionization, the epoch when ultraviolet radiation from the first stars and galaxies ionized the universe's hydrogen, could have been the kill switch. As this radiation flooded space, it heated the remaining pristine gas, making it too energetic to collapse into new stars. In this scenario, population 3 formation didn't taper off, it slammed shut, like a door sealed by the very light these stars created. Supporting this idea are simulations showing that reionization timing aligns suspiciously well with the predicted end of metal-free star formation. The cosmic dawn might have been a double-edged sword, its light both illuminating the universe and extinguishing its earliest stellar pioneers, yet the evidence is maddeningly indirect. The last population 3 stars likely formed in isolated pockets, regions so remote that they avoided contamination from early supernova or the reach of reionization's radiation fronts. These holdouts could have persisted hundreds of millions of years longer than their peers, like lone embers glowing in the ashes of a bonfire. Some astronomers even speculate that a few might have survived to the present day, hidden in the Milky Way's halo or drifting between galaxies. The hunt for them is fierce, with telescopes scouring ancient metal-poor stars for traces of population 3 ancestry. Finding one would be like discovering a living dinosaur, a relic of a bygone era frozen in time. The stakes go beyond mere chronology. If population 3 stars faded gradually, it implies the universe's chemical enrichment was a slow, steady process. But if they vanished abruptly, it suggests pivotal moments when cosmic conditions shifted violently, rewriting the rules of star formation overnight. JWST deep surveys may soon settle the debate, searching for metal-free stars or their remnants in galaxies at the edge of observable time. Until then, the fate of these stellar pioneers remains a haunting question, not just about how they died, but about how the cosmos grew up around them, turning their fiery end into the seeds of everything that followed. The first supernova weren't just spectacular finales for the universe's earliest stars, they were the ultimate cosmic alchemists, transforming the pristine emptiness of space into a chemical playground. When these titanic explosions ripped through the darkness, they scattered heavy elements like cosmic graffiti, painting the cosmos with the first traces of carbon, oxygen, and iron. But the patterns they left behind aren't what we expected. Instead of smooth, even distribution, the early universe's pollution resembles a splatter painting, some regions drenched in metals, others eerily untouched. This isn't just chaotic randomness, it's a forensic record of how the first stellar death shaped everything that followed. Take the case of the Milky Way's oldest stars. Some, like the ancient SMSS 03136708, contain barely a whisper of iron, just 1/10,000,000th the abundance found in our Sun. Others, like He 13272326, are shockingly metal-rich despite forming only slightly later. This stark disparity suggests the first supernova didn't spread their ashes uniformly. Instead, their debris must have traveled in concentrated jets or bubbles, enriching patches of space like cosmic fertilizer while leaving adjacent regions barren. Computer simulations reveal why, unlike modern supernova which explode into a galaxy already full of gas and dust, the first detonations happened in near-empty voids. Without surrounding material to slow them down, their ejector could have raced outward in narrow streams, creating pockets of extreme enrichment surrounded by vast chemical deserts. The real enigma lies in the outliers regions where elemental ratios defy all expectations. In the dwarf galaxy Segway 1, astronomers found stars with bizarrely high levels of strontium and europium but almost no barium. This signature doesn't match any known type of supernova. The closest analog, so-called collapsar explosions, where massive stars collapse directly into black holes, ejecting material from their poles in focused jets. If these events were common among population 3 stars, they could explain not just the odd chemistry, but also why some areas appear untouched. A jet pointed in one direction would enrich a narrow cone of space while leaving the rest pristine. But there's a twist. Some ultra-distant quasars show evidence of ion enrichment earlier than should have been possible, hinting that supernovae weren't the only polluters. Could primordial black holes, voraciously devouring gas and spewing out heavy elements, have contributed? Or might dark matter annihilations have generated exotic isotopes that blended with stellar debris? The answer might lie in the rarest of cosmic relics, hypermetal poor stars that formed from nearly pure supernova ejecta. These celestial time capsules, like SDSS J00180939, preserve the elemental fingerprints of individual explosions. Their chemistry suggests some first-generation stars may have exploded with energies far beyond modern supernova, perhaps even as pair instability, events so powerful they left no remnant behind, only a fleeting chemical signature etched into the cosmos. The legacy of these explosions isn't just written in stars. Intergalactic gas clouds analyzed through quasar absorption lines reveal traces of oxygen and carbon stretching billions of light years, the ghostly afterglow of supernova whose light faded eons ago. Yet even here, the distribution is patchy, with some clouds showing 10 times the expected metal content. This clumpiness challenges our assumptions about how turbulence and cosmic rays mix material across space. It's as if the early universe had invisible walls, corralling metals into certain zones while keeping others clean. Solving this puzzle isn't just academic. Those first uneven sprinklings of heavy elements set the stage for the diversity of planets, life, and even the galaxy clusters we see today. A slightly different distribution might have left the cosmos permanently barren, or alternatively, seeded life far earlier. As telescopes like JWST trace these chemical trails back to their sources, they're uncovering a story far richer than we imagined. Not a tidy narrative of gradual enrichment, but a chaotic, dramatic saga where the universe's first explosions wrote their rules in stardust and fire. The universe we see today is a tapestry of light and shadow, vast threads of galaxies woven into a cosmic web, with enormous voids stretching between them like empty rooms in an infinite mansion. But this grand architecture didn't emerge fully formed. Its blueprint was written in the faintest ripples of density left over from the Big Bang, fluctuations so subtle they were little more than quantum whispers in an otherwise smooth early cosmos. The mystery lies in how these infinitesimal wrinkles grew into the filaments, clusters, and voids we observe today. Were the first stars and galaxies simply passive passengers riding the currents of dark matter, or did they actively reshape the cosmic web's birth? Dive into any modern simulation of the universe's growth, and you'll see dark matter's invisible hand at work. those primordial density variations imprinted in the cosmic microwave background acted as seeds, with slightly denser patches pulling in more dark matter through gravity. Over billions of years, these regions evolved into sprawling filaments, where galaxies now gather like beads on a string, and voids where matter was siphoned away, leaving behind cosmic deserts. The first stars didn't just light up randomly, they ignited along these developing dark matter highways, tracing the earliest outlines of the web we see today. Their formation wasn't an accident, it was destiny written in the gravitational code of the universe. Yet observations keep revealing surprises. Some galaxy clusters appear more tightly packed than simulations predict, while certain voids stretch larger and emptier than they should. This suggests the cosmic web's growth wasn't just a smooth, linear process. Radiation from the first stars and supernova might have played an overlooked role, their ultraviolet light heating surrounding gas and pushing it out of voids, accelerating their evacuation. Meanwhile, supermassive black holes in early galaxies could have unleashed powerful jets, carving channels in the intergalactic medium and redirecting the flow of matter like cosmic plows. The web isn't just a fossil of dark matter's influence, it's a palimpsest with layer upon layer of stellar and black hole activity etched into its structure. Even more intriguing are the hints of something deeper patterns in the web that precede the first stars entirely. Detailed maps of galaxy distributions reveal faint echoes of sound waves from the universe's infancy, oscillations frozen in time when the cosmos was a seething plasma. These baryon acoustic oscillations should have imprinted a preferred scale on the cosmic web, a kind of universal fingerprint. But some recent surveys suggest deviations, as if unknown forces, perhaps even exotic dark matter interactions, tugged at the web's threads before stars had a chance to form. The James Webb Space Telescope is now peering into this formative era, searching for the moment when the cosmic web transitioned from a theoretical framework into observable reality. By analyzing the arrangement of the earliest protogalaxies, astronomers hope to catch the web in its infancy, not yet the intricate lattice we know today, but a simpler skeleton, frail and incomplete. The answer won't just reveal how the universe built its grand design. It'll tell us whether the first stars were mere bystanders or active architects, shaping the cosmos even as they shone for the very first time. Globular clusters today are like cosmic retirement homes, dense spheres of ancient stars orbiting galaxies like silent relics of the past. But rewind to the universe's infancy, and these clusters might have been stellar nurseries on steroids, where the first stars were born packed shoulder to shoulder in seething, ultra-dense environments. The idea flips everything we know about early star formation on its head. Instead of solitary giants flickering to life in isolation, the cosmos's first light could have ignited in frenzied clusters, their collective radiance piercing the darkness like a chandelier in a void. Simulations reveal just how chaotic these environments would have been, with thousands of massive stars crammed into a region smaller than today's solar system. Gravitational tugs and radiation wars would have been constant. Stars might have stolen material from one another, grown unnaturally massive, or been hurled into space as rogue runaways by close encounters. The chemical fallout would have been equally extreme. Supernova in such tight quarters wouldn't just enrich nearby gas, they'd flood it with metals, creating overlapping shock waves that could trigger new waves of star formation almost instantly. Imagine a chain reaction of stellar births and deaths, each explosion seeding the next generation in a frenzy of creation. But here's the twist: if these clusters existed, where are their remnants? Modern globular clusters are too metal-rich to be direct descendants, and searches for pristine, ancient analogues have come up empty. One possibility is that they didn't survive. The sheer violence of their surroundings, supernova blasting gas away, black holes merging and devouring neighbors, might have torn them apart within a few million years, scattering their stars into the cosmic wild. The only traces would be faint chemical signatures in the Milky Way's oldest stars, whispers of a time when the universe's first light burned brightest in crowded, desperate brilliance. Another camp argues the opposite, that early stars preferred solitude. Without heavy elements to help gas cool and fragment, protostellar clouds might have struggled to collapse into multiple stars at once. Observations of the most metal-poor stars support this. Many show elemental patterns suggesting they formed in isolation, far from the polluting winds of clustered neighbors. Yet even this view has holes. Some ancient stars, like those in the Segway one-dwarf galaxy, display bizarrely high carbon and nitrogen levels, a possible smoking gun for having formed near massive, fast-living stars that polluted their birth clouds before vanishing. The answer might lie in the middle. Perhaps the first star clusters were rare but monstrous, their influence disproportionate to their numbers. A single densely packed nursery could have peppered the early universe with heavy elements, while most stars formed in quieter pockets. Telescopes like JWST are now hunting for the telltale glow of these clusters in distant galaxies, searching for regions where ultraviolet light crowds into unnatural brightness. Meanwhile, theorists run ever more detailed simulations, testing how quickly gravity could corral primordial gas into such dense knots without the help of metals. What's at stake isn't just a census of early stellar neighborhoods. If clusters dominated, they'd have turbocharged reionization, flooding the cosmos with radiation far faster than lone stars could. Their supernova might explain the universe's patchy chemical enrichment, and their black hole mergers could be the missing seeds of today's supermassive giants. The silence of empty space might not be empty at all. It could be the echo of a time when stars didn't just light the universe, but did so in a blaze of crowded, short-lived glory. Quantum mechanics and cosmic expansion might seem like worlds apart, subatomic uncertainties versus galaxy-spanning structures, but they're intimately linked. The cosmic web's vast filaments and voids, stretching across billions of light years, trace their origins to fluctuations tinier than an atom, imprinted in the universe's first moments. According to inflation theory, these microscopic quantum ripples were stretched to cosmic proportions during the Big Bang's explosive growth spurt, becoming the seeds for all future structure. Yet when astronomers measure the distribution of galaxies today, some overdensities appear curiously extreme, as if inflation's magnifying glass didn't just stretch those early fluctuations, it amplified them beyond prediction. The discrepancy centers on something called the power spectrum, a statistical map of how matter clumps at different scales. Inflation forecasts a specific pattern. Smaller fluctuations should dominate, with their strength tapering off smoothly toward larger scales. But observations reveal anomalies. Galaxy clusters like El Gordo and the Boots Void, for instance, are so massive and empty respectively that they strain the upper limits of what inflation should allow. It's as if someone turned up the volume on certain cosmic frequencies while leaving others untouched. One explanation suggests inflation wasn't the uniform process we've assumed. Brief phase transitions during this period, like bubbles forming in boiling water, could have created localized surges in density, leaving behind pockets of space primed to grow into today's most extreme structures. Dark matter adds another layer of intrigue. If certain types of dark matter particles interacted weakly with each other or with radiation in the early universe, their collisions might have reshaped the initial quantum noise. Think of it like a sculptor adding subtle grooves to a block of marble before the chisel strikes. These tweaks could have steered gas into unexpected configurations long before stars lit up. Some models even propose that dark matter's gravitational pull wasn't uniform. Instead, it clustered in ways that exaggerated certain fluctuations while suppressing others. The result, a cosmic web with filaments thicker and voids emptier than the simplest inflation models predict. The most radical solutions venture beyond established physics. Could primordial black holes formed not from stars but from direct collapses in the early universe have acted as gravitational anchors, pulling matter into premature clumps? Or might cosmic strings, hypothetical defects in spacetime left over from the Big Bang, have carved channels where galaxies later formed? These ideas flirt with the edge of known science, but they're not purely speculative. Gravitational wave detectors like LIGO could one day catch echoes of such phenomena in the faintest ripples of spacetime. The James Webb Space Telescope offers another angle. By mapping the earliest galaxies, it might reveal whether these anomalies were baked in from the start or emerged later. If overdensities appear fully formed in the universe's youth, it points to inflation's quirks. If they grow over time, dark matter's hidden dynamics likely played a role. Either way, the answer won't just explain why the cosmos looks the way it does, it'll expose whether quantum mechanics and gravity conspired in ways we've yet to imagine. The quantum origins of cosmic structure aren't just a footnote in astrophysics. They're the missing link between the universe's smallest beginnings and its grandest designs. Every photon we detect has traveled a finite distance across the universe, carrying stories from its origin, but the oldest light we can possibly observe dates back just 13.4 billion years. This cosmic horizon isn't just a technical limitation. It's a fundamental barrier written into the fabric of spacetime itself. Beyond this point, the universe was so dense and opaque that light couldn't travel freely, trapping everything in a foggy void. Yet hidden in that uncharted darkness lies the holy grail of cosmology, the moment the first stars flickered to life. If we can't see past this wall with light, how do we reconstruct those missing chapters? One audacious approach bypasses light entirely, turning instead to gravitational waves, ripples in spacetime generated by cataclysmic events like colliding black holes. These waves travel unimpeded through even the densest plasmas, meaning they could carry information from before the cosmic dawn. Proposed missions like the Laser Interferometer Space Antenna (LISA) aim to detect primordial gravitational waves, potentially uncovering echoes of population, three stars collapsing, or even earlier phenomena like cosmic inflation. It's like switching from a flashlight to a seismograph, feeling the universe's vibrations instead of relying on its glow. But gravitational waves aren't the only workaround. Neutral hydrogen from the cosmic dark ages emits a faint radio signal at a wavelength of 21 centimeters, a fingerprint stretched by cosmic expansion into today's meter-long waves. Projects like the Hydrogen Epoch of Reionization Array HERA and the upcoming Square Kilometer Array SCAR are tuning into this static, hoping to map hydrogen's distribution before stars ionized it. The challenge: this signal is buried under a cacophony of terrestrial radio noise and astrophysical foregrounds billions of times stronger. Extracting it is like listening for a single violin in a hurricane. Then there's the ghostly neutrino, a particle so elusive it passes through entire planets without a trace. The universe's first supernova would have blasted out neutrinos in unimaginable numbers, some of which might still be drifting through Earth today. Detecting these cosmic relics would require next-generation observatories like the Deep Underground Neutrino Experiment (DUNE), with tanks of liquid argon buried miles underground to catch the rare interaction. Success would give us a snapshot of stellar deaths from the universe's infancy, but the odds of capturing a 13-billion-year-old neutrino. Astronomer David Schlegel likens it to finding one specific grain of sand on all of Earth's beaches. Perhaps the most radical idea involves quantum entanglement. Theorists like Laura Mersini-Horton propose that the universe's earliest quantum states might have left imprints on large-scale structure, an idea dubbed cosmic bell tests. By studying anomalies in the cosmic microwave background or galaxy clustering, we might infer conditions before the opacity barrier. It's a long shot, but if proven, it would mean the universe encoded its own origin story in patterns we're only now learning to read. The irony is palpable. The very expansion that reveals the cosmos to us also hides its beginnings, stretching light beyond visibility while offering alternative messengers, waves, whispers, and quantum hints to fill the gaps. Pushing past the 13.4 billion year wall isn't just about building better telescopes, it's about redefining how we observe. Every workaround forces us to ask, what else might we be missing, and what invisible threads stretching back to creation itself are we only beginning to grasp? The atoms that make up your body, the oxygen in your lungs, the iron in your blood, the calcium in your bones, have a lineage stretching back to the universe's first stars. These primordial giants didn't just light up the cosmos. They forged the very elements that would one day become planets, oceans, and life itself. But tracing their material across 13 billion years isn't as simple as following a cosmic paper trail. The journey from a population 3 supernova to the carbon in your DNA is a saga of chaos, chance, and celestial recycling on a scale almost too vast to comprehend. Start with the explosions themselves. When the first stars died, their deaths weren't tidy. Pair instability supernova, the kind theorized for stars above 100 solar masses, would have vaporized themselves entirely, scattering their heavy elements in spherical shockwaves at nearly 10% the speed of light. But smaller population 3 stars might have collapsed into black holes, their outer layers ejected in lopsided jets. In both cases, the newly minted elements wouldn't have spread evenly. Some regions got a metallic windfall while others remained pristine. Simulations show these ejecta plowing through surrounding gas, sweeping it up like snow in front of a plow, creating turbulent bubbles of enrichment where second-generation stars could later form. The smoking gun lies in the oldest stars still shining today. Metal-poor stars like He 1523090-1, found in the Milky Way's halo, contain barely 1/10,000th the iron of our Sun, yet they're not entirely pure. Their atmospheres harbor trace amounts of carbon, oxygen, and even uranium, elements that could only have come from a single prior generation of stars. By analyzing these ratios like cosmic DNA tests, astronomers can reconstruct the explosions that seeded them. For instance, excess R-process elements like gold and platinum suggest nearby neutron star mergers, while an overabundance of alpha elements oxygen, magnesium points to core collapse supernova. But how did these atoms eventually reach us? The answer involves galactic cannibalism. Over billions of years, the Milky Way devoured smaller dwarf galaxies, absorbing their stars and their elemental legacies into its halo. Some of these captured stars, like those in the Segway 1 dwarf, are nearly as old as the universe itself. Their composition suggests they formed from gas enriched by just 1 or 2 population 3 supernova, making them time capsules of the first stellar deaths. Other atoms might have hitchhiked across galaxies via hypervelocity stars, objects flung out during gravitational encounters, or been carried in the tendrils of the cosmic web, flowing along dark matter filaments. The final link in the chain, star formation in the solar neighborhood. 5 billion years ago, a cloud of gas laced with generations of stellar debris collapsed to form our Sun and its planets. Meteorites preserve this history. Grains of silicon carbide and nanodiamonds within them predate the solar system, carrying isotopic anomalies that fingerprint their origins in ancient supernova. Even more direct evidence comes from Earth itself. A 2017 study found traces of iron-60, a radioactive isotope only made in supernova in deep-sea sediments, suggesting a nearby stellar explosion just a few million years before the solar system's birth. So yes, you are literally made of stardust, but not all stardust is equal. The iron in your blood likely passed through multiple generations of stars before becoming part of you. The gold in your jewelry might have been forged in a neutron star collision that predated the Milky Way, and some atoms, perhaps a few carbon nuclei in your fingertips, could be direct survivors of the universe's very first stars, their journey ending only when they became part of you. The proof isn't just in the stars, it's in the mirror. Every element heavier than helium is a scar from the cosmic battles that lit up the dark. From the birth of the first stars to the hidden fingerprints of dark matter, these 30 mysteries aren't just isolated curiosities, they're interlocking pieces of the universe's greatest puzzle. Each unanswered question, from the bizarre maturity of early galaxies to the ghostly absence of pristine gas clouds, reveals how much we still don't understand about cosmic dawn. The hunt for population 3 stars rewrites the rules of stellar evolution. The uneven spread of the first heavy elements exposes the chaos of primordial supernova. And the cosmic web's quantum origins remind us that the largest structures trace back to the tiniest fluctuations. Every enigma cracks open another door, revealing new layers of complexity beneath what we thought we knew. What's astonishing isn't just the scale of these mysteries, it's how they feed into one another. Solve the riddle of supermassive black holes' rapid growth, and you might unlock clues about reionization. Pin down the true nature of dark stars, and you could rewrite the timeline of galaxy formation. Even the failures, the searches that come up empty, like the missing dwarf galaxies or the elusive lithium, force us to innovate, building sharper telescopes and bolder theories. Astronomy thrives on these gaps in understanding because every "we don't know yet" is an invitation to dig deeper. The next decade promises breakthroughs we can barely imagine. The James Webb Space Telescope is already peeling back layers of cosmic history, while upcoming observatories like LISA and the Square Kilometre Array will listen for gravitational waves and ancient hydrogen whispers. But here's the thrilling part: for every mystery we solve, new ones will emerge. What if JWST spots a galaxy so early it defies all models? What if dark matter turns out to interact in ways that upend particle physics? The universe has a habit of surprising us just when we think we've got it figured out. So as we stand on the edge of these discoveries, let's not just ask which puzzle will be solved next, let's wonder what we haven't even thought to question yet. The story of the first stars and galaxies isn't just about the past. It's about our future understanding of everything from black holes to the nature of time itself. The cosmos began in darkness, then sparked to life. In a way, we're still chasing that first light, and the journey is just getting started.